Hello, I'm Amir Hussain, and in this video I'm presenting our paper on Ricci curvature and the reliability of causal inference on networks. Causal inference is critical for decision making, and it is particularly challenging on network treatment units, and evaluating the reliability of the outcome of causal inference methods is fundamentally challenging, partly due to the fundamental problem of causal inference, which says from the two potential outcomes we could only observe one of them. Therefore, in most cases we don't actually have true ground truth when it comes to estimating causal parameters. We connect graph geometry with causal inference and show that we can use Ricci curvature to predict the reliability of causal estimates on networks. As this diagram shows, there are connections between Ricci curvature, entropy, and system robustness, and on the other hand, between distribution robustness and causal inference. We reformulate some of these connections to establish a direct link between Ricci curvature and causal inference reliability. You can refer to relevant sections in our paper for more details on how we establish this link. The problem we have in hand involves a network of treatment units, for example, a social network of individuals, where each node is an individual and they just show, for example, friendship relations. We estimate a causal parameter on each node, for example, the individual treatment effect, and we are interested in knowing how reliable are the causal estimates we calculate. In this paper, we establish a theoretical connection between graph Ricci curvature and causal inference reliability. We show that this connection is observed in empirical data, where Ricci curvature can indicate the accuracy of causal estimates, and based on this understanding, we propose a Ricci flow adjustment to improve the accuracy of causal estimates by flattening the network. Ricci curvature measures how much the local geometry deviates from being Euclidean, and this can be extended to graphs to capture the extent of dispersion or volume change through an edge. For example, in a tree-like graph, edges have negative curvature, like a hyperbolic space. A grid is a flat graph, and a dense graph, like a clique, has edges with positive curvature, like a spherical space. We also know that Ricci curvature is linked to system robustness. On the other hand, we can formulate learning causal parameters as distribution robust estimation. So we have these two notions of robustness, one linked to Ricci curvature and the other to causal inference. We know positive Ricci curvature leads to more robust system. We show that it also leads to higher distribution robustness and therefore more reliable causal estimates. So our main theoretical result is that positive Ricci curvature makes accurate causal estimation more likely. This implies that we can use the Ricci curvature to evaluate the reliability of causal estimates on networks, and our experiments show that we can empirically observe a negative correlation, as you can see on these plots for 9 real-world networks, between the Ricci curvature here on the y-axis and the error of causal estimates here on the x-axis. Now, can we use this to improve the accuracy of causal estimates on networks? First, keep in mind that most empirical networks are sparse, which means many edges have negative curvature, and we know that negative Ricci curvature could lead to more error in causal estimates. So if we flatten the network, it should improve the accuracy of causal estimates, and we can see that this is actually the case. We propose applying Ricci flow to flatten the network as a pure processing step, and then use a graph neural net based causal inference method to estimate the causal parameter on each node. And we show that this can substantially reduce the error of individual treatment effect in empirical networks, as you can see in this table on the last row. So to conclude, we establish a connection between the reliability of causal estimates on network treatment units and their graph geometry. This gives us a computational tool to evaluate the reliability of causal estimates on networks without any ground truth and independent of the causal inference method used. And based on this understanding, we propose a method using the Ricci flow to reduce causal estimation error. Our method improves the accuracy of causal estimates, and it is a pre-processing step, so it can be combined with any causal inference method. But on the other hand, it cannot target specific neighborhoods, and because it is a pre-processing step, it cannot be updated during training. But perhaps the most important consideration is whether it makes sense to change the edge weights through this method, considering the application that you have in hand. So whoever wants to use this method should ask themselves whether it makes sense to effectively alter the graph by applying Ricci flow to change the edge weights before applying the causal inference method. That depends on the problem you have in hand. If you are interested to learn more about our paper, you can refer to our paper using this QR code. And thank you for watching this video.